the limits is 0.015 y, and the maximum is going to 0.035 meters. Okay, so we are going to calculate the shear stress distribution equation, right? Okay, so that's it. So why we divide this section is because the thickness is going to be constant. The thickness is equal to 0.16 meters. So the shear stress distribution equation is divided based on the thickness that you have. Okay, not because I divide there because it's a web and that's a flange. No. Okay, because from here to here, the thickness is what? Constant. Later on, I'll write another one from here to here. The thickness is what? Constant also. Okay, so now we are just looking at the top flange. Okay, we are just looking at the flange. Okay, so the limits is 0.015 up to 0.035. Okay, so like anything else, right? So we know the shear stress equation is equal to VQ over IT, right? We know V is constant, right? So I highlight this is constant, this is constant. Thickness is also constant because our thickness is defined as what? So the only thing we have to find what is Q. Okay, so QZ, I better write in proper terms because I told you guys that this is VY over IYY. Okay, Q, oh, sorry, IZZ. QZ divided by T, right? So QZ will equal to be width multiplied by depth multiplied by Y bar, right? So based on the distribution, this is our Y value. Okay, what it is a variable. Okay, so our width is a constant. Okay, our width is equal to 0.16. Our depth, if this is our Y, right? This distance from here to here is our what? It's our depth. Yes or no? Right? So to find our depth is equal to 0.035, okay, minus Y. Okay, so this is the width and our depth, and the Y bar, okay, our Y bar is equal to 0.035 plus Y multiplied by half. Some of you might say, hey, Eugene, this is way too fast, right? Why is that? Right? Why is it is equal to the Y bar? So Y bar is where? So this is our Y bar. Okay, so the distance. So if that's our Y, this somewhere in between, not somewhere exactly in between, this is our Y bar. So you ask me, why Y bar is like that? Okay, I'll explain to you why. I don't want you all to memorize. Okay, now let's say we have a rectangular now. Okay. And this is 2 and this is 4, right? Now, what if now our Y is at where? It's at 2. So this is 2. Somewhere in the center is our Y bar. Exactly at the center is our Y bar, right? So can someone tell me what is the Y bar equal to? Just by observation, can someone tell me?
3.
3. How do you get 3?
4 minus
it's somewhere in between, right? So the formula for Y bar is equal to 2 plus 4 multiplied by half. So this is equal to 3, right? Now, if this is 9 and this is 4, what is it? Can someone tell me? So it is equal to Y bar.
6.5.
Yeah, 9 plus 4 times by half is equal to 6.5. So this is why it is like this. Okay, that's it. Because this is our y, right? The y bar, this is our y bar, this is our y, and that's it. Okay. Listen, I'm not smarter than you. I believe God gave us equal intelligence. Okay. I'm only more experienced. That's it. Okay. And I'm as I say, I'm close to 50. Okay. I want you to have this knowledge before you guys become 50. Okay. Make you guys better than me. Minus y squared. And some of you might say, Eugene, you're nothing but full of shit, but whatever. Okay. So this will be equal to 0.08 times by 0.035 squared. So it's equal to 98 times 10 to the power minus 6, right? Minus by 0.08 y squared. Okay. So this is our equation number 1. Now, how do we know that this is correct? Can someone tell me how do I know that this is correct? Anyone? So to only know whether you're correct, you should substitute y must be equal to 0.035 meters. The q, z must be equal to 0. Right? Because at y, if y is equal to what? This is at y is equal to 0.035, right? There's no area, okay? So this is the check, right? So 98 times 10 to the power minus 6 minus by 0.08 multiplied by 0.035 squared. It has to be equal to 0. Okay, I don't know. Okay, so 0.08 times by 0.035 squared is equal to, yeah, it's equal to 0. Okay, this is how you check. Okay, so from here, it is so easy now, right? So the shear stress as a function of y, we are looking at the flange. So this will be equal to V, which is equal to 90 times 10 to the power 3. The centroid is 5.813. Right? The thickness, right, is a constant, right? The thickness is a constant, and then all you need to do is multiply 98 times 10 to the power minus 6 minus by 0.08 y squared, right? So when you formulate everything, so 90 power 3 times 98 power minus 6 divided by 5.813 minus 6 divided by 0.16 is equal to 9.483 times 10 to the power 6 minus 90 power 3 times by 0.08 divided by 5.813 power minus 65.16. 7.741 times 10 to the power 10 to the power 9 y squared. Okay, so this is your shear stress distribution, right? So if you substitute y is equal to 0.035, okay, the shear stress will be approximately equal to 0. Okay. So the next thing that we're going to do, right, we are going to consider, okay, so we are not over yet, okay. We have to consider, I'm going to copy again. Right. We are going to do this section now. Okay. We are good. So we have done here. Next, we are going to do here. Okay. So this will be from 0 to 0.015 meters. Okay. So I'll call this our top web. And the bottom one, I call it the bottom web. Okay. So the top web, okay, is the same thing. Okay, nothing changed. Okay, the first moment of area, we have to be careful. Okay, so for the top web, our limit is 0, y, and you go to 0.015. Thickness is constant. The thickness is the twice of 0.02. Right? So the constant, the thickness over here is equal to 0.04. Right? Again, Q is the one that is going to be affected. Now, the Q is different now. Okay, I'll show you. So the Q will be the Q of the flange plus by the Q of the web. Okay, Q of the flange. So you have to consider, I'm going to draw the boundaries that you have to go. So if you look at it, okay, we are consider this entire region now. Okay, so now we are having a slider now. This is our Y, right? And then we have our Y bar. Okay, so look, let's do the flange. So the Q of the flange, so the width, remember when I calculate Q, I always do this. I always do web, depth, then Y bar. Okay, so the width is 0.16. The web is 0.02. Why that's the case? Because now the variable is from 0 to 0.15, right? It's only considering the web. The flange is a constant now. Okay. And then our Y bar will be equal to 0.035 minus by 0.02 divided by 2. Okay. Now we calculate for our web. Okay, we calculate for our web. So plus twice because of left and right. Okay. Then the width is 0.02. Right? And then the Y bar or the Y is equal to 0.015 minus by Y. And the Y bar is equal to 0.015 plus by Y multiplied by half. So you can see the trend, right? You minus here and then you plus here and then you just multiply by what? By half. Likewise over here, right? You minus over here, you plus over here, you multiply by half. Okay, just follow that trend. Okay. So from here, this will be equal to 0.035 minus 0.02 divided by 2 times by 0.02 times by 0.16. So the first term is 80 times 10 to the power minus 6. Right? And then we have a plus. You have a plus by 2 times by 0.02 times by 0.5 is equal to 0.02. So the half can cancel with 0.02 multiplied by 0.015 squared minus by y squared. Okay. So it will be 0.015 squared times by 0.02 plus by 80 power minus 6. So it's equal to 84.5 times 10 to the power minus 6. Okay. And then minus by 0.02 y squared. Done. Okay. So your shear stress now, okay, as a function of y is equal to 90 times 10 to the power 3 divided by 5.81. I can't remember again. 5.813 times by 10 to the power minus 6 multiplied by 84.5 times power minus 6 minus by 0.02 y squared. And the thickness we declare is equal to 0.04. Okay. So this will be equal to 90 power 3 times by 84.5 power minus 6 by 5.813 power minus 6 divided by 0.04. It's equal to 32.707 times 10 to the power 6. Okay. And then minus divided by 84.5 power minus 6 times by 0.02. 7.741, okay, times 10 to the power 9, okay, y squared. Okay, so that is for the top. Now, for the bottom web, okay, the bottom web will be really quick, I promise you that, okay. So we're going to do for the bottom web. Okay, we're going to do for the bottom web. So this is what we call our bottom web. Okay. So now you all know the procedure. So it's only the first moment of area. So I'm going to do the bottom web. Okay, so bottom web. So it's going to go from 0 y bar, and because it's 35, it's going to be 65 millimeters, 0.065. Okay, because the distance from here to here is 65 millimeters. So I'm going to do the bottom web. Okay, so we know the thickness is also twice of 0.02. Okay, so the Q of the bottom web is equal to what? Okay, so width times depth multiplied by y bar. Okay, so so twice because of left and right. Okay, the width is 0.02. The web is equal to 0.065 minus y, right? 0.065 plus y multiplied by what? So this will be equal to, so this is equal to 0.02 multiplied by 0.065 squared minus by y squared. Okay. So this is equal to 0.065 squared times by 0.02 is equal to 84.5 times 10 to the power minus 6 minus by 0.02 y squared. Now, did you all see this number before? Anyone?
Yeah.
Can you all see that? So if you take your analysis from the top or from the bottom, right? The first moment of area is the same. Yes or no? This is Q from bottom. This is Q from the what? The top. This is because the first moment of area about the centroid, either from the top or bottom, is the same. Okay, mathematically. Okay, so from here, the same thing. Okay, the shear stress y as a function of y at the bottom web, right? At the bottom web is equal to. So I can cut and paste this thing. It's the same equation. Okay, it's the same equation. Okay, that's why, listen, this course, okay, what I told you when we start, you have to trust the what? You have to trust the math. Okay. Now, there will be a quiz. Okay, and the quiz is also due on Friday, and it's about shearing stress. Okay, and please attempt it. Please try and do it. Okay, and I know it's going to be a very hectic week for you guys, but focus. Okay, and yeah, this will be included in your term test, and your term test will stop there. And I've already posted the homework already. Okay, if that's the case, I'll still be around. Okay, and this is the end of class. Okay, thank you.
Quick question, sir. Which chapter is this chapter 2 or what chapter in the book?